Now, this is the second part of the lecture, and tonight we're covering two topics. The first was non-laminar flow. Now we'll talk about material balance. Chemical engineers, 1 and 2. Okay? In the simplest sense, what is material balance? It's a molecule by molecule accounting formula? Or is that how you think of it in chemical engineering, or do you think of it as a species accounting or just mass accounting? Molecule by molecule. You okay with that, Mr. Bake? Not really? Pounds or kilograms or something? Okay. Or what's those funky things, moles? So if we're counting moles, then that's really molecules, right? But a material balance is some sort of a molecule by molecule accounting. So when you look at these kinds of equations, you have to ask yourself, what are they really showing? Well, what we're showing is that there are withdrawals, there's expansion, there's the expansion of the water, there's expansion of the rock, there's water influx. All these different possibilities for mass coming in and out of the system. How many of you were alive in 1980? Nobody. No? You like that? I made you laugh. That's good. How many of you know what the first song played on MTV was? Come on, Joker. Yep, yep. Oh, we had different MTV in India. Yeah, I got it, okay? Yeah? Why do I even bother? Alex? Cameron? Gabe? You're my last hope, Eric. Nobody's looked it up on the internet yet? Video killed the radio star. Video killed the radio star. Is that on Grand? Yeah, I think Grand Theft Auto actually came a little later. You know, back in 1980, for me, the video game that we had in 1980, it was called Pong, okay? And you played it on TV, and you went zip, 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 zip with a little knob. So, simulation killed the material balance star. Simulation killed the material balance star. What am I really trying to say here? Gabe's getting a kick out of this. That was a gas equation. This is the oil equation. By the way, let's do a really quick discussion of this. This is a constant compressibility case for material balance. And so this is pressure drop. This is oil in place. This is compressibility. This is formation volume factor, initial formation volume factor, NP. If we solve for NP over N, that is delta P times C multiplied by BOI over BO, if we solve for NP over N. What's another name for NP over N? Recovery factor. What's the maximum recovery factor for a black oil? If I say P bar is equal to 0, which is not, I know I'm violating a whole bunch of things, but let's say that I take this to 0 pressure and I multiply PI multiplied by total compressibility multiplied by initial formation volume factor divided by initial formation volume factor. What kind of number are we going to come up with? Cam, you want to try it? Give me a number. What's your favorite number for PI? 5,000? Okay. What's your favorite number for CT? 10? And just to be easy, we'll say BOI over BO. Just to be easy, we'll say it's approximately 1. What's that number, class? 5 times 10 is 2. Are you really sure you want to be a petroleum engineer?
I know, but I just did the math wrong.
Yes, I know you did the math wrong. Now try it again. It's 5%. So the drive energy from fluid expansion only is 5%. Mr. Bake, how does that affect your research? Not sure. He's not sure. But the energy in the fluid itself, depending on how much energy there is in the fluid, 5% recovery. Now, of course, we benefit greatly from having gas coming out of the solution and providing additional energy, because how many of you had Dr. McCain? Nobody, right? Yeah, Dr. McCain has a great quote about the only place where Mother Nature takes her feet off the ground in petroleum engineering is at the bubble point. Why? There's a jump discontinuity and compressibility at the bubble point. How big a jump, Alex? No hobble English. Ladies? Don't know. Petroleum engineers? It's about 5 to 7 as much as 10. So you gain that much energy when you hit the bubble point. That's how much more energy there is in the gas. Okay, still not enough. If you did a calculation with the equation below it and allowed yourself to have a gas profile, you're probably looking at another 10%. So primary recovery, oil expansion only 5%, oil and gas expansion 15%. All these forums and all these workshops and all these other things that talk about 70% recovery factor. How are you going to get 70% recovery factor? Sorry? You're going to have to put energy into the system. What's our primary mechanism of putting energy into the system, class? Injecting something. Water, CO2, lean gas, wet gas, something. And you're going to have to keep doing it. You stop, it dies. There's also thermal effects. There's also surfactant, chemical effects, other things. Is it going to be easy to get to 70% recovery? No. It's going to be really hard, and it's going to be expensive. It's probably impractical. In 1991 or 1992, there was a book issued by the National Academy of Engineering in the United States, National Academy of Science, National Academy of Engineering, on the so-called Taurus data space, which was the West Texas carbonate oil fields. They estimated 300 billion, that's with a B, barrels of oil were left behind. 300 billion with a B. And just so everybody's on the same page, that's not what we're producing now. Those reservoirs are still there. What we're producing now is the source rock, the underlying shales. It's not uncommon for there to be 100 million barrels of oil in place per section per 640 acres. That's a lot of billions of barrels, people. 5% recovery. 5%. Petrophysicist, you don't sleep so good when you hear that. Doesn't care. Yep.
So what's the mean by having more
So,
reducing the pressure?
okay, when we go below the bubble point, we produce gas. But I'm saying that above the bubble point, that's the first equation. That if we pretended that we produce no gas, what's our maximum recovery with bubble point energy only? Or sorry, with fluid expansion. When we go below the bubble point, then we have the support of the gas. Now you're thinking of the nanoscale effects where you're suppressing the bubble point, where you're actually pushing it further down in pressure. I hadn't really thought about whether that's going to help or hurt. I guess it would hurt, but well, I guess it would help as well, because once you start producing gas, gas is going to be preferentially produced. So I could see the logic of bubble point suppression being a good thing. Okay. The next slide is probably the most important thing you've read in class so far. If you're going to write a book, you need to put something really annoying in it. And this was buried in his book. Cameron, read it out loud for everybody. Yep. I want you to read it with passion. Pretend it's Shakespeare. It seems. No,
to apply the concept of material balance to oil fields, belief being that it has now been superseded by the application of a more modern technique of numerical simulation.
okay, pause. What's he saying? Simulation killed the material balance star. Simulation killed the material balance star. How many people do material balance? Nobody. The data that you need for material balance, is it the same or different than what you need for simulation? Same. So why do material balance? Any error in your assumptions or in your setup for the material balance is going to give you the wrong answer. What's going to happen in the simulator? You just keep adjusting things until you're happy with it. What were you saying you hated about that room? Okay, Gabe, read the rest of it.
Acceptance of this idea has been a tragedy and has robbed engineers of their most powerful tool for investigating reservoirs and understanding their performance.
Stop. That's a pretty bold statement. How many of you like to hunt? Nobody. You don't count, Eric. You like a lot of things. How many of you like to fish? Okay. So, how would you go fishing without any fish hooks or string? Sorry? Flashlight and dynamite? Okay. How do bears do it? Mr. Bake? They sit in the water and they just knock the fish on the bank. Is there an analogy with this? He's saying you gave up the old tool for some modern newfangled thing. Okay? Gabe, keep reading. Imposing their wills. What a strange choice of words. Read it again.
Rather than imposing their wills on them, as is often the case when applying numerical simulation directly in history.
Who's doing numerical simulation in this class? Nobody? Cameron. That makes you the expert because none of them will admit it. Did you impose your will on the data? You damn right you did. You did it and you don't apologize for it. Pretend. Oh, so you didn't pass.
No, that was the best history match you'll ever see, but it was after about 100 hours of re-simulating it over.
So you imposed your will eventually? Is there a comma or a pause?
Took a beating doing it.
Okay. How do you guys feel about this? This is a major crossroads in your life as a reservoir engineer. Are you going to let the data talk to you? Or are you going to make the data dance? Anybody? This is a really important moment. I've spent the entirety of my career analyzing and interpreting data. I let the data talk to me. When I was your age, I had a choice to make. I almost went into simulation, but my personality's not right for it. I really tried. I had a project and I had all sorts of other things lined up, but I believe the data should tell us. And that's when I fell in love with well performance, or it fell in love with me. But now, you can't tell the difference. When you're performing an analysis, the simulator is as fast as you can move the mouse. So is it imposing your will? Is it interpretation? Is it analysis? What is it? It's complicated. You guys are lost, aren't you? I'll make it up to you, I promise. But what I'm trying to tell you is Material balance, there is no analysis. The data tells you what it's doing. What's the easiest way to break something complicated? How many of you want to have a Ferrari or a Lamborghini? Yeah? Okay. How are you going to pay for the gas? I'm just curious. Have you ever put diesel in a gasoline car? Gasoline in a diesel car? What do you think is going to happen if you do? Yeah. So what's the easiest way to break something complicated? Give it some garbage. Is material balance tolerant of garbage? Yeah, because it does only one thing. Well, what about simulation, Mr. Liu? When you give simulation garbage, you have so many knobs, you can turn garbage into something else. Correct. You have to be very careful. A lot of quality control, a lot of quality assurance exercises. But material balance doesn't ask, it demands that the data be a certain way. You must account for masses, all masses, water, gas, oil, masses that are generated, masses that are consumed, masses that are, well, you can't destroy it, but however you want to think about it. And what's the key variable in a material balance equation? I know I'm talking to you and I'm not showing you lecture notes. You know what I'm asking for. Somebody show me their phone. What if you could buy a phone that you never had to recharge? Would you buy it? Anybody? Okay. Why do you have to recharge your your phone? You run out of energy. Okay. You know how when you're driving or maybe flying, you're watching your fuel gauge all the time? Maybe you're not, but I do. What's your fuel gauge in a reservoir? Pressure. You never waste pressure. By the same token, the most critical variable, I know everybody else says it's masses, but to me, the most critical variable in material balance is pressure. Why? More importantly, it represents the average energy in the system. The word average is essential. Material balance has no dimension. It is a zero-dimension tank. The energy in the system is represented by the average reservoir pressure. You must know the average reservoir pressure. You must know all of the masses that were injected to, taken out of, whatever the term may be. But ultimately, you must know average reservoir pressure. I just mentioned all this. And this is a diagram taken from Amix, Bass, and Whiting that shows the initial condition of the reservoir. You have some water that isn't moving. You have an oil zone. You have a little bit of gas in contact with it. And then you have a gas zone. Oops. And you have some water in the gas zone. And then when you produce, when you lower the pressure, when you take fluid out, the gas zone expands slightly, the connate water expands slightly, the volume of oil is reduced, the volume of gas increases, the connate water expands. Why does water expand? It is slightly compressible, very slightly. And then what is encroached water? It's water that moved into the system under external energy. External energy. What is rock expansion? The rock actually has compressibility as well, so it expands. All of these are sources of energy. They're your fuel gauge. You have to watch them at all times. How do you calculate average reservoir pressure? Well, in 1938, the kidney bean reservoir, I guess this looks more like a pork chop, but whatever, it started out with a few wells and they had some spot pressure measurements. What are spot pressure measurements, Alex? It's where you go out and read the gauge. Okay. And then in 1940, they have a lot more wells and they're reading more pressure measurements and they've contoured the pressures. Then 1941, I don't know why they reduced the number of wells. I guess these are the only wells they have that actually have pressure, so they're contouring those. So they went around and they checked the pressure in these wells. These are spot pressure measurements. By the way, what company is the only company in the world that does a spot pressure measurement on every well twice a year? Nobody knows. Saudi Aramco. And why do they do it? Because that big giant book that Texaco, Chevron, and Exxon left them on page number 433 says take a spot pressure flowing bottom hole pressure measurement. So they have 3 crews, maybe more now, driving around taking measurements. Actually, they don't do that anymore. Why not, class? Because they have at least 1 pressure gauge in every well, usually 2. And what else do they have? A downhole flow meter, because they're the only ones that can afford them, right? Okay, so now we keep going. Now it's the 25th of July, and then it's right after Pearl Harbor here, and then a little bit later on, maybe another year later, and you can see they're drawing contours. How do you estimate the average reservoir pressure with these spot pressure measurements? Anybody? Technically, the average reservoir pressure is the pressure integrated over the volume of the reservoir, correct? Averaged over volume. Do we know the volume of the reservoir? Do we know the volume under which that particular pressure is being compared, applied, represents, whatever? No. What do we know? We know the total production of the field, and we know the production at that well. What's blasting game rule number 0? Cheat. So how do we cheat? We take the pressure at the well, we multiply by the cumulative production at that well, then we add up all the others, divided by the total cumulative production. That gives us some sort of average pressure. Okay? But technically, the average reservoir pressure in the system should be static. The system should be static. The system should be static. One more time. The system should be static. Average reservoir pressure, the system should be static. Are we going to shut in the entire field to take pressure measurements? No. So what do? We cheat. We take spot pressure measurements. We hope they're correct. Are spot pressure measurements too high or too low? They're too low. So coming back to our friends, we take a quick look. And this is a chart, if you want to call it that, from 1942 to 1950. They track the oil rate. They track the water rate. They track the gas-oil ratio. They track the number of wells, so the number of wells went up and it stayed constant. And then they track the reservoir pressure. Oops, they made a mistake because they went, this value is lower than that. The average reservoir pressure during production should do what, class? Decrease monotonically, right? That's okay, though. A little bit of mistake isn't going to kill anybody. Now, look at all the water that comes on production. And they have the pressure actually going back up. Do you think the pressure is actually going to go back up from encroached water? Shouldn't. But injected water, of course. But encroached water, no. Okay. This is a very simple graphical explanation. And I know you're saying, but Tom, we have all that data. We have the number of wells. We have the production, water, oil, and gas. But the critical one is that black line labeled pressure. All of those go in the material balance calculation, and if you don't have that black line, you're not going anywhere. So again, we talk about the black oil, and again, we talk about the dry gas. And in the general gas material balance equation, there's this funky pressure-dependent compressibility. Very quickly, this is what happens whenever there's a system compressibility effect. There's also the gas produced, which is withdrawal, the gas injected, which is what's injected. There's a water produced term, which is water you can measure. Here's the water produced term again. Here's water injection, and here's WE. What is WE, class? You've been taught it's called water influx. Can you taste water influx? Can you smell water influx? Can you measure water influx? No. It is an inferred variable. It is an inferred variable. It is an inferred variable. We cannot measure WE. Okay? So how do we use the full material balance equation? What do we do for WE? Alex? We cheat. How do we cheat, Eric? We substitute a model for WE. We can substitute the Eric model. We can substitute the Sarkar model. We can substitute the Wan model. Okay? What's the Eric model? What might be some sort of weird power law relationship? What's the Sarkar model? The Sarkar model may be the assumption of an outer reservoir, a giant donut of an aquifer. And how do we know what that behavior is? Well, we know what that solution is, so we can apply it to that. Can someone think of another one? If you searched on water influx, water encroachment, etc., 10 years ago, you would have probably gotten almost 1,000 SPE papers. There have been a lot of papers written on water influx. It's a great problem because nobody knows what the answer is. Is that going to keep you awake tonight? Who's got a background in numerical analysis? Anybody? No? How come people invent things? Why did they invent the wheel? Why did they invent fire? Well, they didn't really invent fire, but kind of came along. What's the stupidest invention we've got? Anything on late night TV? What? Come on. Throw me a bone here. Eric, you were saying something. I apologize. I was in the country of Iran about 20 years ago, well, 17 years ago, and I attended a Master of Science presentation, and they were solving this equation. And they did something that I never thought of. What did they do? They treated WE as an independent variable that was time dependent, and they solved for it step by step with simulated annealing. So they just sent it to this program, and it iterated and iterated and iterated, and then it produced a curve for WE. No model, just a value. Is that a good idea? Well, it was different. But what you ended up with was WE going up and down. WE doesn't go up and down. It only continues to increase. What were they picking up? They were picking up the error in all the other measurements. Pretty clever, huh? That's why every time I hear big data, I want to know what the hell they're doing. A few weeks ago, I got in a lot of trouble. I used a microphone. I said something I shouldn't have. Somebody said, what's going to happen with all these big data methodologies? And I turned to the audience of several hundred people and I said, what I find is whenever you expect big data to solve the answer, you don't know what the question is. And the chief technologist of ConocoPhillips sent me an email that he wasn't very happy with that because they've invested tens of millions of dollars in this. The point is, you can trick an algorithm, right? So this is what the compressibility factor versus cumulative gas looks like. That's, sorry, did I miss it? I got to go all the way back to the top. My apologies. So this is the dry gas case. P over Z is equal to PI over ZI, 1 minus GP over G. Now if I go back down, it's easy to see. And I know the people in distance learning land are going, stop doing that, you crazy coot. Okay, I got it. So if we start with this equation and we just start eliminating things, we say that this CE term is 0, then that kills that thing multiplied by 1. If we say that that's 0, that's 0, that's 0, that's 0, that's 0, then we end up with a very simple P over Z. Now, I mentioned the abnormal pressure material balance equation. This was derived by Fetkovich. There's a variation of it given much earlier than that by Dake. I think that's the generally preferred form. What Fetkovich was really trying to show was what all the different components of that effective compressibility function were. And that was very noble, but it was kind of impractical. In other words, we don't really need this form of the equation. We had the Dake form, but this form kind of tries to explain things. It turns out that the behavior of the abnormally pressured case looks like a quadratic, that PI over ZI is basically related to a function of GP squared. Okay, we'll talk about that. And then there was another case where we were looking at just the water influx. No abnormal pressure effects, no water production effects, no gas injection effects, etc. Just WE. And I had a student who ran approximately 1 million simulations. Okay? Wrote a simulator and ran them. And what we came up with is, I thought that this would be a relationship that had only a single parameter relationship, like an alpha. Unfortunately, it turned out to be an alpha and a beta, which meant we couldn't reduce it. So we took something that we thought was going to be simplified, and it ended up still being relatively complicated, and we couldn't solve it. Turns out he did some work recently in the last few years. It's been out of school 12 years, something like that, but he still tried. And it turns out the behavior is more power law than anything else. So there may actually be a way of getting around the WE. There may be a mathematical trick that we can use to do that. So again, the first case is PI over ZI versus gas produced. And this is a simulation case, so everything is a perfect straight line. The gas in place is predicted by this trend, no problem. Okay, it's a little bit low. It probably has something to do with maybe something he simulated, the student that is, but it's slightly low, maybe, what's that, 40, so 3 or 4% low, something like that. Okay. This is the famous Anderson L case, SPE 02938. This is a South Texas gas case. This is not complicated. This is a well in a single fault block in South Texas and low permeability gas reservoir. They took the pressure data, not religiously necessarily, but relatively speaking, we think these pressures are representative. And so I had a student who came to me and he said, I think there's two trends. There's a trend like this, and then there's another trend that looks like this, more or less. And what happens when you think you have those kinds of trends, class? Well, imagine that you're standing on a balloon. I'm standing here putting my weight on this. The fluid is supporting, the gas is supporting the weight of the overburden. And then once you let some out, and then it's sitting on the matrix, you get the blue line. So the red line is where the gas is basically supporting the overburden. It's overpressured. And then the blue line is where the matrix is supporting the overburden, and it behaves like any other non-stressed case. So that student drew that up. And we were presenting this work in his MS defense, and one of the professors says, "This doesn't help me." Why doesn't this help you? Think like a professor. Why doesn't this help you? Because you have to see the second straight line. Okay? If you see the second straight line, it's too late. Now name the places in the world where you're going to have relatively high productivity cases like this with abnormal pressure effects. U.S. Gulf Coast, offshore Nigeria, offshore Angola, other places like that, right? Why? Why are the pressures so high? Why is there abnormal pressure in U.S. Gulf Coast? You get this right, I'll let you go. Where's my geologist? Petrophysicist. What's the largest river in the northern hemisphere? The Mississippi River. It's dumping an enormous amount of sediment into the Gulf of Mexico. That sediment is relatively young. It does not have time to come to hydrodynamic equilibrium. So it's overpressure. Okay. Very quick. Alex Gas Company. Ready? You come to Tom the banker. I loan you the money to drill and complete this well. You come to me and you tell me you've got 120 billion cubic feet of gas. I'm pretty happy. I'm thinking, I'm going to make my money back. Then you come to me and tell me you got 72 billion cubic feet of gas. What am I going to do? Well, I can't kill you, and I can't really do anything else bad to you, but I'll never loan money to you again. And this is exactly what happened. There were a lot of operators in the Gulf Coast that thought they had much larger gas deposits than they did. And the reason I kept asking you what the cross point between the red and the blue is, you still haven't figured it out? That's a hydrostatic pressure. That's the equivalent normal pressure that should exist at that point. It's so easy and so obvious, nobody thought about it. But a young engineer by the name of Raj Prasad wrote a paper on this, and he did nothing but show on the graph where the hydrostatic pressure should be. He had all these different cases. We should have listened then. Okay. All right. I will see you on the 2nd of October. Alex will do math lecture tomorrow night and Monday night, and I'll see you on the 2nd of October.